in the last class we had discussed about the micro pumps, the configuration of the micro pumps, the overall evolution of the micro pump, and then we also had some discussion about the overall characteristics of the micro pump. So, what are the different sub elements of a micro pump which are available, and how a micro pumps are designed for with reference to different configurations. Like we had some discussion about this modes, including the absorbing mode and the release mode, and then we also had some discussion about this valve and a valveless pump, etc. Now, in today's lecture, so we will discuss about the other configurations of a micro pump, and we will also discuss about some of the case studies relevant to the micro pump. So, as far as micro pumps are concerned, like based on the actuation domain, appropriately we can classify this micro pump. So, one such classification includes the electromagnetic micro pump. So, as far as this electromagnetic micro pump is concerned, as the name suggests, so these electromagnetic or the magnetic micro pumps works on the principle of generation of repulsive and attractive forces between the permanent magnet and drive coil on the application of electric current through the drive coil, which in turn oscillates the diaphragm or the membrane. So, ideally we have two conditions. One is a kind of an ideal condition, like if you see the overall configuration of this. So, there is a kind of an embedded magnet in place, there is an inlet wall and an outlet wall which is available, and then inside these embedded magnets. So, in the ideal condition there is going to be a flow, and then when we try to energize this magnet, appropriately we can have a control over the diaphragm. So, in the case of an inlet, so this inlet valve opens and appropriately there will be a kind of a an absorbing condition will happen, and then there will be a kind of an outlet valve which exists. So, now if we closely observe the overall actuation mediums or the actuation switch which has a control over it is, one is the drive coil and the other one is a diaphragm which exists, which is going to be a kind of an embedded magnet. So, like here we have two conditions. So, one is a kind of an ideal condition which is used for pumping, and then there is going to be a kind of a condition where an absorbing condition will happen, where through the absorption the liquid is being fed into it, and then we will be having the release condition. In the case of a release condition, the outlet valve will open and appropriately the liquid will be pumped to the desired system. Now, the next configuration we can consider a simple rotary micro pump. So, as far as these rotary micro pumps are concerned, so these are kind of a dynamic micro pump which is worked by adding a kinetic energy directly to the fluid through moving boundaries or to fields. So, these dynamic pumps maintain a continuous flow through a momentum transfer, and it requires a higher operational speed, and it also requires a precise fabrication tolerance. So, when we try to talk about the higher operational speed and precise fabrication tolerance, it basically depends upon the inlet, and then it basically depends upon the outlet configuration. So, based on the direction of the rotation, so appropriately we can have an inlet phase which is being flowing through it, and then there will be an outlet phase which exhibits. So, appropriately it tries to move through this particular system. So, these kind of rotary based micro pumps are efficiently used for creating a certain amount of vacuum or a certain amount of configuration in such a way that a kind of vacuum will be created, and then there will be a continuous movement or the continuous flow of the liquid from one region to the another region. So, that is the reason these kind of rotary pumps are called as a dynamic micro pump, and it gives a kind of a kinetic energy directly through the fluid which is moving along the boundaries of the field. Now, let us discuss about one more configuration which is called as a thermopneumatic pumps. As the name suggests, so there is going to be a thermal system in place, and then there is going to be a pneumatic system which exhibits over here. So, due to the variation in the thermal property, so appropriately there is going to be a displacement which exists. So, in the case of a thermopneumatic structures, a phase change actuation of the micro pump works on the principle except for the medium which is used for the actuation. So, that is, there is going to be a kind of a continuous thermal expansion and contraction of air or phase changing material in the secondary chamber, which exerts a pressure onto the diaphragm, which causes it to deflect, or it gives it gives an indication for an appropriate vibration. So, in this particular aspect, if you see, so we have a kind of a two different condition. One is called as a ideal condition, another one is called as a dispensing condition. So, in the case of an ideal condition is there is going to be an air chamber which a pumping arrangement which is available. Then there is going to be an inlet wall. Through the inlet wall there is going to be an absorption, and through the outlet wall there is going to be a dispersion. So, this fluctuation between the inlet and the outlet wall is taken care by the heating coil which is available. So, by supplying a heat to it, so appropriately a pumping behavior exists. Based on the pumping behavior, the inlet and the outlet condition can be displayed. Okay. So, in this particular aspects, so there is going to be a drive coil, and then there is going to be an air chamber which exhibits over here, and then there is going to be a diaphragm arrangement with a pumping chamber. So, this dispensing condition, in the case of a dispensing condition, these kind of diaphragm is going to be efficiently used for deployment or for release of the fluid appropriately. So, in the case of these drive coils, like if you try to closely observe the diaphragm perspective point of view, so the diaphragm gets actuated because of the thermal heating or the thermal displacement. Okay. So, like appropriately the diaphragms are selected, either in several cases such kind of diaphragms, bimetallic based diaphragm structures are deployed. In some cases we might be having a thin metallic sheet where the expansion and contraction of these metallic sheets are being deployed. So, only key parameters which affects these particular diaphragm, which basically includes the thermal conductivity and the specific heat capacity of the material, has a high influence on developing such kind of diaphragm, thermal based diaphragms or thermo-pneumatic based diaphragms. Okay. Now, let us talk about the shape memory alloy. So, as far as these shape memory alloys are concerned, so we already had several discussions on shape memory alloys, either it is in the form of a bulk phase or it is in the form of a kind of a thin film base. So, as far as these shape memory alloys are concerned, so the actuation of this micro pump through a shape memory alloy is either through a thermal or sometime it might be through a magnetic force. So, that is, so when we consider a magnetic force, so instead of a shape memory alloy, so we will be using a Huesler alloy. So, the main actuation medium for this Huesler alloy is, like when we try to supply a kind of a cyclic loading, cyclic magnetic field to it. So, appropriately there will be an expansion and the contraction which exhibits on these particular structures. Okay. So, as far as these actuations are concerned for a shape memory alloy, so we have a kind of a switching between the austenite behavior and a martensite behavior. So, based on the switching between the austenite behavior and the martensite behavior, appropriately there is going to be a kind of an actuation which exits, and there will also be a kind of a deflection which happens. So, when we closely observe or when we have a control over this solid phase transition between the austenite phase and the martensite phase, so appropriately it has a kind of a flexibility for us to move or to appropriately have a control over the actuation behavior in this particular process. That is, we can, if we try to tune the temperature property of it, so appropriately we can have a control over the actuation behavior. Then with reference to strain perspective point of view, a mechanical strain can be developed during this phase transition, which result in the deformation of the micropump membrane. So, in this micropump membrane, so what happens is we have a kind of a shape memory alloy based structure, and then when we try to actuate it, this micropump membrane moves back and forth, and appropriately there is going to be a deflection which exhibits, and from this deflection we can have a control over the suction and the relief. Basically, we can have a control over the absorption condition and the dispensing condition. If you remember, so we had discussed about this concept called shape memory alloy biomorph. In the case of shape memory alloy biomorph, we have seen that there is a shape memory alloy structure is integrated with a Kapton polyamide. So, the actuation happens in such a way that the one way of actuation is taken care by the shape memory alloy, and the return stroke is appropriately taken care by the Kapton polyimide. So, what happens is when the Kapton polyimide will take care of the return stroke and the main level actuation is taken care by the shape memory alloy. So, the kind of a actuation frequency can be appropriately exhibited using this system. So, like when this actuation frequency, so that appropriately we can have a control over the actuation frequency as well as the actuation displacement. So, ideally it is a kind of a thermal based system, and the phase transformation of this thermal based system are taken into consideration. Okay. Now, we can consider this the next level of system is called as a electrostatic based micropumps. So, as far as these electrostatic based micropumps are concerned, so it basically like we had discussed about this comb drive actuators, where there is going to be an electrostatic charge which is going to get generated. From this electrostatic charge, it is expected that there is going to be a kind of a resonant frequency which exhibits, or a kind of a micron level displacement can be controlled by these electrostatic charge. So, as far as these in these electrostatic charge, the force of attraction and repulsion generated between the electrodes which actuates the flexible diaphragm. So, upon application of electric potential across the electrodes attached to the membrane and the pump body, the generated electrostatic force causes the diaphragm to flex, causing a change in the chamber volume which increased and the pressure decreased, resulting in the flow of the fluid inside the chamber. So, if we closely observe the overall attracting force and the absorbing condition, so there is a diaphragm in place, then there is an electrode in place. So, we have an inlet wall and an outlet wall. So, through the inlet wall we are trying to look into the pumping behavior, and the electrode is going to get actuated and the diaphragm is going to get actuated into it. Now, in this particular process, so what we have seen is, so we have a diaphragm and then there is an electrode in place, and the electrode is going to and the electrode is deployed. So, in these regions exactly the electrostatic charge are going to get participated, and when these charges get participated, it gives a kind of an efficient flexibility for the movement of the electrode from position A to position B appropriately. So, interesting part of these electrostatic charges are that you can generate a high frequency using this system, and then inappropriately dispensing conditions can be deployed. Okay. So, if you closely observe the overall subsystems of these electrostatic pump, so there is going to be an inlet arrangement and valve arrangement, a diaphragm arrangement and an electrode arrangement. So, the application of this like actuation of this electrode will help for a appropriate movement. Now, let us see some of the different configurations which exhibits for developing such kind of micro pump with reference to different chamber configuration, which we had seen when we try to look into the classification perspective point of view. So, with reference to chamber configuration perspective point of view, the micro pump is classified into two. One is called as a single chamber configuration, and the other one is called as a double chamber configuration, which is a kind of a parallel connection. Okay. So, in the case of a single chamber configuration, so there will be an inlet port and an outlet port. So, we have a diaphragm in place which is being integrated with the chamber. Through the inlet, the liquid is made to pass through it, and there is going to be an actuation which exists, and through this actuation the outlet is made to feed into it. Whereas, with reference to double chamber parallel connection perspective point of view, so we have a chamber 1 in place and a chamber 2 in place. So, liquid is made to feed into this inlet through chamber 1, and then so we have two inlets and two outlets. So, there are two chambers which are being placed over here. So, this two chambers will try to vibrate and then will try to oscillate at a higher frequency, and you get a outlet coming out of it. Okay. So, wherever you need to work upon mixing up of the fluid, or when you want to work upon two different types of fluid, such kind of double chamber based parallel connections can be deployed. Now, this is a kind of a configuration which we call it as a double chamber series connection. So, as far as in this double chamber series connection is concerned, like a chamber 1 comprises a liquid and the chamber 2, and it will be pumped to the chamber 2. In the meantime, chamber 1 can again collect the liquid and then it can move to chamber 2. That is like for instance, so if I want to disperse a particular fluid at a particular frequency or with a particular time interval, such kind of double chamber based series connection systems can be efficiently deployed for an appropriate dispersion. Now, this is a completely kind of a different configuration, where let us consider there are 3 chambers are there. The inlet is connected to chamber 1 and the outlet is connected to chamber 3. So, the pumping is happening in such a way that the pumping is fed in such a way that through the inlet the pumping is fed and then it is passed through the chamber 2. So, in the chamber 2 what happens is there is going to be a certain amount of mixing which exhibits, and after this mixing, so this system is made to push through chamber 3, and from the chamber 3, so you are trying to move to the outlet system. So, what is happening is from the chamber 1 we are trying to collect the fluid, and then it is stored in chamber 2, and once again through the chamber 1 again a suction happens and then it is made to pass through chamber 2. So, due to the variation pressure difference between chamber 1 and chamber 2, this liquid which is available in chamber 2 will try to move to chamber 3, unless and until a pressurized fluid is made to move to chamber 2, appropriately there will be a kind of a flow through this outlet. So, in this case also, like wherever we need to have a mixing up of a fluid or wherever we need to have a different time delay, appropriately such kind of peristaltic pumps can be deployed. Now, let us see some configurations of let us see some of the different configurations or different types of valves which exhibits. So, as far as valves are concerned, already we have seen a configuration with reference to valves micropump and a valveless micropump. So, we have seen a comparison with reference to valve micropump and a valveless micropump. So, in the case of micropump valves, the flow rectification which converts the non-directional flow to a directional flow, the selection of the flow rectifications depends upon closing up pressure, response type, micropump efficiency and the material capability. So, as far as in this particular case perspective point of view, so there is a ball arrangement where there is a flow direction is there. So, through this flow direction, so we have a ball in place, and in the flow channel there is going to be a no flow direction through which the ball moves. Okay. So, the control of the flow or the movement of the overall pressurized fluid is well taken care using this ball valve. Then there is a kind of a dynamic geometry valves which exhibits. So, as far as in this dynamic geometry valve is concerned, we can classify this dynamic geometry valves into 2. One is called as a bridge type dynamic geometry valve, another one is called as a cantilever type dynamic geometry valve. In the case of a bridge type check valve, so there is going to be a slot kind of arrangement. So, like wherever we need to have a no flow direction, appropriately the bridge will move, and wherever we need to have a flow direction, appropriately the bridge will rotate. The same configurations or the similar functionality can be deployed by a kind of a cantilever type configuration. So, in the case of cantilever type configuration is concerned, so we will be having a cantilever type of arrangement. So, this cantilever type can be used for opening and closing of the valve. So, wherever there is, so in this particular case, for example, if there is going to be a high pressure and low pressure, appropriately the cantilever will open up and close up based on the requirement or based on the flow direction. Now, there is a kind of configuration which is called as a static geometry valve. So, as far as in this static geometry valve is concerned, so there is going to be a conical nozzle and a diffuser. So, there is going to be a nozzle action and a diffuser action. So, within this nozzle action and the diffuser action, appropriately 2 important parameters can be controlled. One is the flow and the other one is the pressure difference. So, as far as flow perspective point of view, like by creating a pressure difference between the nozzle action and the diffusion action, appropriately we can have a control over the flow. Okay. Or by giving a different pressure difference, appropriately we can have a control over the flow. Now, these kind of geometric valves are basically classified based on the configuration or based on the type of the geometry. So, based on the type of the geometry, if you observe, so we have a conical nozzle or a diffuser which is available. So, the nozzle action will work and the diffuser action will work. So, between the nozzle action and the diffusion action, appropriately the flow moves. Similarly, there is a kind of a trapezoidal nozzle diffuser is there. So, as far as this trapezoidal nozzle diffuser is concerned, so like based on the overall like geometry or the appropriately we can have a different flow control or we have a different diffusion control. So, let me just take you around the different diaphragm materials and their overall property. So, as far as in this diaphragm material is concerned, so this is a kind of a static material which exhibits, and these are the different diaphragm material which is nothing but an actuation material which exists. Now, if we try to consider a glass, so the different materials which includes the glass, the PDMS, the silicon wafer, the electropolymer, the stainless steel, brass, polyamide, rubbers, Nephron and acrylic elastomers are being efficiently used. As far as actuation principle perspective point of view, we have the piezoelectric structures, we have electrostatic structures, we have a electromagnetic based system, thermopneumatic based system, phase change materials are also available. So, in addition to this, we have also seen this configuration of this thermopneumatic structures, how it is being deployed. As far as thickness perspective point of view, in most of the cases it ranges from 0.01 to 0.4 is the overall configuration, and these are some of the basic properties of these materials which exhibits. Now, let us discuss one case study where a kind of a micro pump is used for a micro robot for a kind of a like endoscopic related applications. So, in this particular process, like the overall thought process is something like this, like suppose if this is an let us consider this as an intestine wall. So, in this intestine wall, so there is a configuration. So, the main focus of this micro robot should move through this intestine wall. So, appropriate actuation needs to be deployed in this particular system. So, the system looks something like this. So, this is a kind of a former cabin, and this is going to be a kind of a hind cabin, and there are two gas bags are there. Okay. So, this is going to create a kind of an inchworm mechanism. So, as far as in this particular case is concerned, like there is so one thing which we may need to consider is there is going to be a kind of a like locomotion which exhibits. So, in this locomotion, so what we can see is like the fabricated micro pump will be assembled in the hind cabin of the micro robot. So, it will be kept over here, and the front and the back bag like surrounding the outer surface of the micro robot will be inflated alternatively to engage the clamping function. So, another linear actuator will be assembled in the front cabin to realize the fore and the after movement. So, the micro robot can propel and bend itself to simulate the inchworm like movement. So, when the gas bag is inflating and clamping, we can like work out the clamping force and then the force which is evolved for flowing through the intestine. Now, this is the overall like structure or the overall final product what is being imagined to move along the intestine related structure. Okay. Now, to make it proper, like the system comprises of a kind of a linear actuator, an air drum, and a small one way valve. So, few researchers they have developed this type of a medical micro pump for a endoscopic robot. So, which is driven by a kind of a linear actuator based on a direct DC motor, and this micro pump consists of two active one way valves and a cylindrical air drum. So, ideally the overall size of the pump prototype will be in the order of 12.5 mm in diameter and 56 mm in length. So, if you see the overall construction of it, so here we will be having the kind of a linear actuator, and then we can have a kind of a, probably I can draw like this. One way valve, the air drum, and the linear actuator. So, the one way valve comprises of something like this, which has a kind of a small gas bag kind of arrangement, and then there is going to be a rubber hose which we call it as air drum. So, this is a kind of a bellow kind of arrangement. This is connected to the linear actuator. So, this is a kind of a linear actuator. So, what happens is the overall arrangement if you see. So, the linear actuator is meant for giving a kind of a motion to the air drum, and this air drum will give a kind of an inch-one mechanism. The overall locomotion happens. So, through this air drum, so we are trying to actuate this gas bag. So, when these gas bags gets actuated, so appropriately we can have a kind of a peristaltic motion in this particular air drum, and then the overall peristaltic motion is controlled by this linear actuator. So, that it moves a kind of it gives a forward motion to the structure, and finally, this kind of structure can be deployed to move into the overall intestine. So, that what happens is there is going to be a kind of a movement, a kind of an inchworm movement which exhibits. So, if we see the overall parameters which are being involved in it, so like so if you see, like it has a kind of a, so we need to count the overall stress set on the intestine canal by the gas system, as well as we also need to consider the overall like configurations which includes the virtual work principle. So, when we try to consider the virtual work principle, following parameters will come into consideration. Like let us consider, so M is the kind of a torque of the DC motor, Fd is the output force, Fd is the output force of the linear actuator, and V is the linear speed of the linear actuator. And eta is the transfer efficiency. So, ideally like in such kind of systems we can get an actuation in the order of few microns, and like if we try to look into the overall design perspective point of view, since it is being it is used for kind of like biomedical related applications, especially in the intestine where it is highly sensitive. So, such kind of airbag kind of arrangement will be highly helpful to give a kind of a inchworm motion to the system, so that we can have a control over the structure. Okay. So, this is a kind of a case study. So, you can refer to this paper to have a much more understanding on it, and in fact, this this system is quite an interesting system, where there are a kind of a linear actuator and a one way wall are appropriately designed, and it is used for the movement of the system. Okay. Now, as far as future perspective point of view, especially in such kind of micropump perspective point of view, there are wide case studies are well projected. In fact, on a biomedical perspective point of view, there is a quite a good amount of micropump developments are being established, especially in addition to this, for space perspective point of view also there is a good amount of micropumps has been established. Now, like when we try to look into the future direction perspective point of view, like advanced materials and fabrications which can be efficiently deployed for developing this micropump, smart and integrated systems can be focused. So, the system should focus upon the low power consumption, and since it has a potential application towards biomedical related applications, like we have seen one particular case study. So, similar to this, we can also focus on some of the other case studies also, like in those particular, so that you can have a more flexibility for biomedical related applications. And most important aspect is with reference to lab on chip integration. Now, like so overall, to summarize with reference to micropump perspective point of view, so we have seen the different configurations of micropump. So, we have seen the overall evolution of the micropump. So, we have also discussed about the different microfabrication techniques which are being employed for micropump, different materials which are being used for micropump. So, like different actuation modes. So, we have seen the different designs where different actuation modes are deployed for taking care of the micropump related development. And then we have also gone through some of the aspects where we have seen that these micropumps are deployed for different functional related applications. So, we have also seen some kind of parametric related applications related to micropumps. In the next module, in the next class, we will be discussing about the micro engines, about the different configurations of micro engines, about the different actuations of micro engines, how these micro engines are being deployed for different applications in detail.